Hello everyone, this is our first video on differential forward and inverse kinematics. The first topic we have to discuss are skew symmetric matrices or asymmetric matrices. So you know, in general, if I have a symmetric matrix, and here we are mostly dealing with 3 by 3 matrices. So if I have a symmetric matrix, then you know that if this is R12, this has to also be R12. So although you might call it R21, but it has to be the same as what? R12. If you call that one R13 and this is R31, they have to be the same. And let me use a different color actually. And so any two elements that are mirror image of each other with respect to the main diagonal, they have to be the same. They have to be equal to each other. Okay, so here we go. This is called the symmetric matrix, right? Each element with the other element of the same color, they have equal values. Now, anti-symmetric or skew symmetric is the opposite. The elements that are mirror image of each other with respect to this main diagonal, they are negative of each other. So if you call this a basically symmetric matrix, right, like S, symmetric means if you transpose it, so if you exchange the rows and the columns, then S transpose is equal to S. Okay, so this is the definition of a symmetric matrix, that the matrix and the transpose of it are the same. But if, on the other hand, the elements that are what? The elements that are mirror image of each other with respect to the main diagonal are negative of each other, as you can see, and also the elements on the diagonal are 0, then we call it anti-symmetric or skew symmetric, which means instead of S transpose being the same as S, S transpose is actually negative of S. And of course, here, if you exchange rows and columns, they are going to get negative, but the only way that these two matrices are the same, because you are negating here all of the elements, right? If you see here, I'm negating all of the elements, including the diagonal ones. So when you set these two equal, then the diagonal elements are equal to their negative of themselves. And the only possible solution for it is they're all what? 0. Okay, so in a skew symmetric matrix where S transpose is negative of S, you can show that the diagonals have to be all 0, and then the mirror image of each other on the diagonal, they have to be negative of each other. Okay, so that's the overall idea of skew or anti-symmetric matrices. Good. Now here we define an operator, skew symmetric on a vector. So for a vector A, which has 3 components, AX, AY, and AZ, I'm defining an operator, skew symmetric matrix operator, okay, which creates a matrix out of the vector. So if my vector A here that you can see, if it has 3 components, AX, AY, and AZ, then the skew symmetric operator that acts on A and gives me a matrix is going to be like this. On the diagonal, it is going to be all 0. On the anti-diagonal, you have negative of each other. But the way that you put AX, AY, AZ is like this. That element, basically 1, 2 is negative AZ. Element 1, 3 is AY. And element 2, 3 is negative X. Okay, so this is how you form it: negative AZ, AY, negative AX, and of course here, if you mirror it with respect to diagonal and negate it, you will get the other elements. Correct? So that's not complicated. So all you need is this arrangement here at this upper triangular portion of the matrix: negative AZ, AY, negative AX. So this is an operator here. We call it the Skew Symmetric Matrix operator. Now, what's specific about this operator is the operator is linear. Which means if you apply it to the linear combination of two vectors, you can show that it is going to be the constant gains, alpha and beta. So alpha and beta are scalars. They can come out of the operation. And this plus and minus, it can even be minus. This plus and minus in general can also come out. Okay, so this operator, this is an operator function, basically. It is linear. But one of the important properties of this operator, why did we define it in the first place? One of the very important properties of this operator is using that you can rewrite the cross product of two vectors as what? As a matrix product. This is one of the most important properties of this operator, because in rigid bodies, this cross product happens a lot. And since here in this course, we are trying to write everything in a matrix notation, so we prefer, instead of having a cross product, we have what? We have a matrix product. And you might say, like, where? Like, for example, if I have, like, for example, a rigid body with 2 points A and B, the relative velocity between B and A is what? So V of B with respect to A, as you know, is what? It is omega of the rigid body cross R of B with respect to A, and that is the vector that connects A to B, this vector. So you see, this relative velocity term is a cross product. So instead of writing it like that, I say, well, for me here, A acts like omega and P acts like that vector. So I can write it as S of that omega times R of B with respect to A. And this omega in general can have what? Omega X, omega Y, and omega Z. So if this omega in general is like, as I said, omega X and omega Y and omega Z, it has all three components, then this guy is going to be what? 3 zeros on the diagonal, negative omega Z, omega Y, negative omega X, and then you have positive omega X, positive omega Z, and negative omega Y. If you multiply that by this R vector, which has three components, X, Y, and Z, you will get the exact same thing as you did the cross product. Okay, and there are other terms too. For example, the acceleration between B and A, the tangential component of it is also alpha cross R of A, B with respect to A. Okay, so here you can also write it as S of alpha times R of B with respect to A. Has to go as subscript. Okay, so this cross product happens a lot in rigid bodies, and since robots are just made of a bunch of rigid bodies, we prefer to convert all of these cross product terms that we use for velocities and acceleration analysis, convert them into a matrix product, and we can do that with the help of this Skew Symmetric Matrix. Also, you can show that if you have a rotation matrix like R and you multiply it by vector A, right? So you know when we multiply a rotation matrix by a vector, we're taken from one frame to another. If you apply this skew symmetric matrix to this rotated version of A, that is the same as if you multiplied the skew symmetric version of A to R and R transpose. Okay? So, for example, this A here can be omega. If you know the omega of the rigid body, right, a portion of the robot, let's say end effector, with respect to one frame, and you want to take it to another frame, right, if you want to calculate that, one way is to get that S of omega form S of omega, and then pre and post multiplied by R and R transpose. And if you remember, we had something when we talked about rotation matrices and what they do in the second video on the channel. You can see that we had something like R inverse times A times R equal B. And you know, since R is a rotation matrix, instead of inverse, you can use transpose. Correct? So if you look, this is very similar to this. And in fact, if you change the order of the R, like for example, if this R is 1 with respect to 0, if you make it 0 with respect to 1, that's going to be the same as this. So you see, this guy is what we call similarity transform. So you can also perform similarity transform by multiplying A by rotation matrix R and then applying the S operator on it. Okay, so you can do this task, similarity transform, using just one product and then creating a S version of the result instead of multiplying it by R and then multiplying it again by RT. So this is faster than this one, the right hand side. And here you go from here to here. Instead of doing cross product, you do a matrix multiplication. So this S operator can basically accelerate or simplify or rewrite some of the formulas that we had earlier for rigid bodies, for transforms, and so on. And it is going to be very useful, especially when we talk about the angular velocities, as we're going to see. So before we get into that, let's just show an example of one of these. Just practice on one of them maybe, and just demonstrate it to you, and then we go and see how we can use it in real action. So here I'm going to say A is, for example, vector 1, 2, and 3. And then P is vector like 4, 5, and 6, right? So what is the cross product of A and P? If you can see, it is -3, 6, and 3. Well, actually -3, -3, 6, -3. Good, so that's cross of A and P. Now what we need is to calculate S of A and then multiply it by P and see whether we get the same thing. Since that is my A, right, this is my A, so S of A is going to be what? It is going to be 0, right? And then if you remember, it's -AZ, AY, -AX, that corner. So let's do it. -AZ, AY, then here this element is going to be mirrored with respect to the diagonal and negated. So you should get a 3 here, a 0, and then this is -AX. Then you have this element being negated, so it is going to be -2. Then you have this element being negated, so you get, well, let me make sure. So this is the same as No, that's -1, so this is going to be +1. So it is like this. Okay, you see it is skew symmetric, -AZ, AY, and -AX. So that's S of A. Now if you multiply S of A by P, S capital A, where P should be P transpose. That's the same as what we had, which was cross of A and P. If you look at them, the result is the same. Right? So that's all it is. Done. You see the result is the same, and you can also do a check on this one as well. Okay, so let's keep the check of that one for later, because it's just multiplying a bunch of numbers and we can easily do that. Let's get to the important application of this skew symmetric matrix that, as I said, it is about angular velocity. So if you remember from rotation matrices, the rotation matrix was an orthonormal matrix, means inverse of it is the same as transpose of it. So if you multiply R by R transpose, the result is identity matrix. Now R is a function of theta or several thetas, and those thetas, the angles, can change with respect to time. So really, you can say that the rotation matrix does have what? Time derivative, because the theta is a function of time. So what I want to do here is to take a time derivative from both sides of this relation. It's a product here, so if you take time derivative, it is going to be the derivative of R, which is R dot, times R transpose, plus R times the time derivative of R transpose. And as you know, transpose and time derivative, I can exchange the order, so it is going to be R dot R transpose plus R times R dot transpose. And this is equal to time derivative of I. Well, I has all constant entries, right? 0 and 1. They don't have time derivative, so the result of this is 0. Okay, so you get to this point. Right? Now, here, this is what I do. I define the first part of this relation to be a skew symmetric matrix S. So I say, how about me calling this part S? Clearly, you see, if that is S, this guy has to be what? S transpose, right? Because when you transpose S, if S is R dot R transpose, when you transpose it, what happens? When you transpose A times B, it is going to be B transpose times A transpose. Not only you transpose them, the order of the product is reversed. So it is going to be R transpose, the transpose of it, times R dot, the transpose of it, which is clearly R dot transpose. So clearly you see why when I call this other one is S transpose, right? So it's very clear. And what is it now? S plus S transpose is 0. That exactly matches the definition that we had for what? For a skew symmetric matrix, or S transpose is -S. So I can say when I called this R dot R transpose a skew symmetric matrix, it was really the right thing to do because it is a skew symmetric matrix. Right? So now I come back to this definition and I say, well, here, this matrix that I defined, R dot R transpose, that is actually a skew symmetric matrix. Fine, it is. Now, what does it have to do with the angular velocity? Well, you can easily show that if this R is what? The rotation matrix, which comes from one or several angles, as I said. When you calculate this result, R dot R transpose, as I said, when you calculate this, it is going to be the skew symmetric matrix, but a skew symmetric matrix of what vector? If you remember, for any vector, we can define what? A skew symmetric matrix, which vector should we plug in into this operator skew symmetric to make this guy here? You can show that it is easily what? It is easily the omega. So basically, if this omega that you have here is like omega x, omega y, and omega z, then the result here is what? 0, 0, 0, negative omega z, omega y, negative omega x. Okay, so if I can calculate this, if I'm given a rotation matrix as a function of some theta, and I plug it here, and I calculate this term, it gives me a matrix, the component of which can give me what? My vector omega. Right? So you see, again, using this skew symmetric matrix, and using this matrix products, I can find my what? Angular velocity. So if the rotation matrix is rotation matrix of what? Some frame with respect to another frame, B with respect to I, E with respect to I, whatever you want to call it, okay? Then omega, so if you don't like B, we can call it E to relate it to end effector. So if my rotation matrix is rotation matrix of end effector with respect to what? With respect to inertial, then this omega that I will get is also going to be what? Omega of end effector with respect to inertial as written in what? In the inertial frame. Okay? So if this R matrix is given to me from my forward kinematics, remember in forward kinematics we find R of E with respect to I. If I plug it into this formula, I can also find what? Angular velocity of the end effector with respect to the inertial. Okay, so far we were talking about position and angular position and linear position. Now we are starting to get into what? Angular velocity and then later linear velocity. Right? And that's why we call it differential equations, because we took time derivative of angular position and we ended up with what? With angular velocity. Now, before I get into the next part, let's practice a little bit on this, okay? So let's apply this formula to some well-known rotation matrix and see whether this one can give me anything meaningful. R dot R transpose. So let's do that. So here, I assume the rotation matrix I have is a rotation of Z and what? Theta, correct? If you remember, it is cosine theta, negative sine theta, cosine theta, 0, 0, 0, 0, 1. Now I form this R dot R transpose, right? That's S based on our definition. Let's do it, see what we get. So first take time derivative. Time derivative of matrix means time derivative of each entry. What is time derivative of cosine theta? Well, based on your knowledge of calculus and applying the chain rule, it is going to be negative of sine theta times theta dot. This is going to be negative cosine theta, theta dot. This is 0. This is cosine theta, theta dot. This is negative sine theta, theta dot. 0, 0, 0, 0. And this one has time derivative of 0, of course. Good. So far, that's the R dot. Multiplied by our transpose. So transpose the R. So it's going to be C theta, S theta, 0, negative S theta, C theta, 0, 0, 0, 1. Correct? Multiply them together. Let's see what we get. So first row times first column. If you multiply, you get a what? You get negative sine theta, cosine theta, theta dot. And then what? Plus, you see here, that's negative sine, that's negative cosine. So it's going to be plus sine theta, cosine theta, theta dot. And then 0 times 0. First row times next column is going to be negative sine squared of theta, theta dot. And then negative cosine squared of theta, theta dot. 0. Then multiply by third row, you're going to get all zeros. Correct? Then go to the second row. It's going to be cosine squared plus sine squared. Second row, second column. Sine cosine minus sine cosine. And then second row, third column, again 0. Then 0 times everything is simply 0. Right? Now if you simplify, you clearly know this is also 0, this is 0, this is negative theta dot, because if you factor out theta dot negative, it's going to be sine squared plus cosine squared, and this is positive theta dot. So if I rewrite it for you, it's 0. Negative theta dot, 0, theta dot, 0, 0, 0, 0, 0. This is the result. Now, if you remember, I said this has to be what? This is S, but S of what? S of omega, correct? That's S of omega. And if you remember, I said S of omega in general is what? You remember, it is 0 negative omega z omega y negative omega x, if you remember. Now compare them side by side, see what the result is. If you compare, you clearly see your omega y is 0. Your omega x is also 0. What is your omega z? If you look, it is theta dot. So what is your omega? It's going to be 0, 0 theta dot. Is that what you expected? Of course. Because your rotation is happening about the z-axis with angle theta, right? So when you're rotating about the z-axis, with angle theta, what do you expect your angular velocity to be? Well, of course, theta dot. About what axis? Z. So you only have omega z to be equal to theta dot, and then no rotation about x and y. So omega x and omega y has to be what? 0. And you see it's exactly the case here. Right? So this very simple intuitive case, which I knew, clearly the answer is absolutely correct. And you can try that if you, for example, try r of x and theta, and apply it to that formula and say S equals R dot R transpose, you easily will see the result is going to be what? If you say this is S of omega, you easily see the result will be something that has only omega x in it. So it is going to be what? 0, 0, 0, negative theta dot 0, 0, theta dot 0, 0, which clearly means that your omega x is theta dot for omega x 0, your whole vector omega is going to be theta dot 0 and 0, which means omega x is theta dot, omega y and z are 0. And if you do a similar thing for rotation y and theta, again, you're going to get something similar, but omega is going to be 0 theta dot 0. So you see, it absolutely makes sense, no worries, right? Now, if you have two consecutive rotations, so your R matrix of, let's say, n effector with respect to inertia is two rotations multiplied, like R of x and theta followed by R of z and phi. So here you have to multiply these together. First, multiply, get the result, and then what? Then plug it into this R dot R transpose formula. So it gives you what? Omega of the end effector. Okay? So here, instead of me going through all of this manually, I would do it using MATLAB, and we'll see what the result is going to be. So sims of theta and phi, and I use T and P to make it shorter. The only thing is, later when I want to take time derivative, you cannot do that, so let me do something else. Say sims theta of t, theta of t and phi of t. Okay, now since they are functions of t, I can take time derivative from them. I can say what is diff of phi of t and t. Okay, it can take time derivative. It doesn't going to give me an error, and I can even define this as a new variable, call it phi dot. Okay, so I can do that. Good. Now that I define it that way, I say R1 is equal to, and then I define this matrix, correct? So that's 1, 0, 0, and then 0 cosine of theta, negative sine of theta. Then you have 0, and then sine of theta and cosine of theta. Okay, so that is your X matrix, and then your Z matrix rotation is going to be cosine of phi of t negative sine of phi of t 0, sine of phi of t, cosine of phi of t 0, and then 0, 0, 1. That's matrix 2. Now I say R equals R1 times R2. So that is your rotation matrix. Clearly you see cosine phi negative sine phi 0. And then you have cosine theta sine phi. Right, sine phi sine theta. Here they both have cosine phi in them. top one is also cosine theta. And finally, you have negative sine theta, cosine theta. Okay, so this is your rotation matrix. And now, as I said, I will say S of omega is equal to R dot R transpose. So I have to take time derivative of this, multiply it by the transpose of this, and then simplify. Okay, and if I do that here, let's do it here. So I say S is equal to what? D, or no, diff of R and T times R transpose. And since it's a symbolic, I use transpose. I don't use single quotation mark, if you remember I told you. Transpose, yes. And this is the result, which is quite large. But then I can ask whether MATLAB can simplify it for me. And I guess it did. Look at that, how big that is compared to this one. Okay, it's way simpler. So it's 0 cosine theta phi dot, 0 cosine theta phi dot. And then sine theta phi dot, followed by negative cosine theta phi dot is 0 and theta dot, and then negative sine theta phi dot, and then negative theta dot and 0. So this is the result, okay? And again, you have to compare this against arbitrary omega. So it has to be 0, 0, 0, negative omega z, omega y, negative omega x, and then the negative of those elements. And then from here, you can get your vector omega, which is what? If you compare side by side, what is your omega x? Theta dot. What is your omega y? Negative s theta phi dot. And what is the last one? Omega z. That is cosine theta phi dot. Done. So if you do a rotation of theta about x-axis, followed by a rotation of phi about the current z-axis, then the angular velocity you have is going to be like that. Okay? Theta dot, negative psi theta phi dot, and cosine theta phi dot. That is your angular velocity. And if you bring more and more, right, add one more rotation matrix, you can still do it. You can still form the R matrix, multiply R dot times R transpose, and then get the components, and that's it, right? So let's say here I had an R3 matrix, and the R3 matrix was a rotation Y. So let's say the sequence is what? ZX or XZY sequence. Okay, XZY, or let's say it's an XZ, let's say it's an XZX sequence, correct? Something that is like a proper Euler sequence. So here I use an R3, but for R3, instead of theta, I use a different angle. So first I need to define that variable. So I say sims of So I'll say psi of theta, psi of t as well. Then I define R3 matrix, which is just like R1, but it has psi in it. It's an X rotation, but with angle psi, not theta. It's the third rotation. And I call it all 3. And now when I say R, I multiply R1 times R2 times R3. So that's my R matrix. It has a bunch of components in it. Now I form S again. It's going to be a huge thing, as you can see. But you can simplify that. And here you get something a lot nicer, except for this last one, I guess. Some of them it can easily recognize, they are easy, like 0, cosine theta, phi dot plus sine theta, sine phi theta dot, no, sine phi, sine theta, psi dot, and so on. So elements as 0, 1, 1, 2, 1, and 3, 1 are not too complicated. Then this element 3, 2 seems like it didn't simplify. It could not simplify it for some reason. And the rest of the elements should be good. It's just this middle element. You see, these guys are good too. Some of these elements it could not simplify very well. And they are not hard to show that, like this one that it couldn't simplify is actually a 0. Okay, so the ones that you really cared about are these 3. This middle one it could not simplify and show it's 0 for some reason. But you really need to focus on this one, and this one. Okay, and if you go back you can see those elements here. So here is omega y, as you can see, omega z, negative omega z, right? So that's your negative omega z, this one here. That guy on that corner is your omega y, which is this one. And then you also have what? You have omega, which one is it? Omega x, right? Which is this guy right below omega y. So let's see if it could find anything for it, or it had a hard time on this. No, I guess it's omega x that it couldn't calculate nicely. For some reason it could not calculate this and show what it is. Yeah, it is a little bit, I guess. It's interesting. Because that's also the same as this element here. For some reason it could not simplify it. Okay, because there are too many sines and cosines, I guess MATLAB Symbolic had a hard time, but you can manually simplify it yourself. It's not easy, it's not hard to show that. So anyways, you see this method is completely working. It is completely showing you how to calculate R, omega, if you know your R. Now, is that the only way you can calculate this omega? No. So, for example, here, you see we involved in too much of what? Algebra to say that if I'm doing an X rotation followed by a Z rotation, first one angle what? If you remember, first one was angle theta, the next one was phi, then that's my omega. But that's not the easiest way to do it, Because this omega that we calculate here, if you remember, it was omega of what? This was omega of the last frame. You might call it E frame, for example, with respect to I in I, correct? This is what we had because this rotation was E of I. Now, is that the only way you can do it? The answer is no. You can do it easier by simply adding omegas together. So addition of angular velocities is quite easier than this hard amount of algebra. And let me show you that. This is significantly simpler than to go through that definition, but now here. So let's look at addition of angular velocity. So what happens really here? I had some initial frame I rotated by angle theta about x. So this is theta, and also theta dot. What it does, it keeps the x the same, rotates what? Y and z. So you will get this frame here. Right? If I draw the original ones, this intermediate frame, you might call it, for example, y1 and z1, and then x1, which is the same as the original xi. Correct? This is the original zi, this is the original yi, and this angle is clearly what? Theta. Right? So that's what you do. Now, about the current z-axis, which is z1, now you do a what? Now you do a rotation with what? With phi and angular velocity what? Phi dot. So what happens now is your z stays the same, but your x and y do rotate. Correct? So x comes something like this, and your y goes something like that. So if this is the original x, and this is the original y, this y rotates to the yi with angle phi, and the original x1 also rotates with phi to this guy, which is xi. And your zi, sorry, e, not I. This is your last frame, e. And this one is going to be z of e, which is the same as z1. So here you went from here to here using rotation z and phi. Right? This is what you have. Now, here you have one angular velocity. Here you have another angular velocity. Can I add them together so that if I want to go directly from here to here, I know it is using what angular velocity it is, correct? Or backwards, right? So it depends on how you want to go. The thing that I'm calculating here is what? Omega of e with respect to I in I. So this is what I'm trying to calculate. Omega of e with respect to I in I. How can I calculate it? Well, what is this first one, this theta 1? This is omega of what? This is omega of frame 1 with respect to I as written along what? So the first one is omega of frame 1 with respect to I, right? That's how frame 1 rotated with respect to I, correct? As written along what? Well, since your rotation is about x1 and x1 is the same as xi, so you can say this theta dot, which is about x1, is the same as theta 1 about xi. So I can say this can also be written as about I in this case. Okay? Right? And what is that here? This guy here is simply theta dot and 0 and 0. Only an x rotation, no y and no z. And again, since my rotation is only along this x here, this vector here that I have, this omega 1 with respect to I. If I decompose this along the axis of frame 1, or I decompose it along the axis of frame I, the result is going to be this one, no difference. Because it has no component along y1 or z1, yi or zi. All it has is along either x1 or xi. So the result is the same. Even if I did this frame 1, still going to be the same thing, okay? So that's the same thing. And then plus what? So this is the first angular velocity. What is this next one? This phi dot that you do, this phi dot, is about what axis? It is about what? It is about z1 or ze, correct? It's not about zi anymore, or xi or yi. So whatever it is about frame 1. So if I write it, correct, I can write it as omega of what? E with respect to 1 as written in 1. Or I can say E as long as it looks like this, 0, 0, phi dot. Correct? Only a z rotation. Now, what's the problem here? The problem is this. If you look, I'm adding these two vectors together, the two motions of the frame E with respect to I. It has two motions. It comes from two omegas. These two omegas, when you add them together, you should get your total omega. With one problem here. The problem is the reference in these two vectors is I. The reference in this guy is 1. And if you remember, I told you can never add vectors that are described in different frames or along axes of different frames together. It's impossible. If this guy was also I could add them. I could add simply these two vectors together. But this is in 1, not in I. How can I take it to I? Right? This is in frame 1. How can I convert it from 1 to I? Well, if you remember, that all comes from what? You are right, from the rotation matrix. So what I need is to multiply this by rotation of 1 with respect to I. When I do that, this takes it back from 1 to I. So this whole thing is actually what now? Omega of E with respect to 1 as written in I. Where omega of E in 1 written in 1 is this vector, and what is R of 1 with respect to I? Well, 1 with respect to I has gone through what kind of transformation? X and theta. So this matrix is what? It is 1, 0, 0, 0, 0, cosine theta, negative sine theta, and what? Cosine theta. And now let's do it, see what you get. So it's going to be theta dot 0 and 0 plus. Multiply this by that, what would you get? The first one is 0. The next one, if you see, is negative sine theta phi dot. The next one is cosine theta phi dot. Add them together, what's the result? Theta dot negative sine theta phi dot cosine theta phi dot. Which is exactly, if you look at the result here, this result is exactly what we got by going through all of that algebra. We formed the R, we took time derivative, multiplied by transpose, set it equivalent to the skew symmetric matrix of some omega, and then got the omega. So you see the results are the same. The results are the same. So which method is easier? Of course, this method. Addition of what? Addition of angular velocities. So if you have several rotations, one after each other, and if you want to find the omega of the total motion, there are two ways to do it. Either first, find the total rotation matrix, which takes you from the last frame back to first frame, find the rotation, and then what? Plug it into this formula. Take time derivative of each and every one of the components, multiply by a transpose, gives you a matrix, set it equivalent to S of some omega. That omega is omega of the last frame with respect to first frame as written in first frame. That's one way, or simply add whatever you have. Just make sure that these reference that you are using to add them, they should all be the same thing. So you need to project some of them back with some rotation matrix before adding them to the rest. And that exactly give you what you want. Okay, two methods that I told you how to get this important thing, omega of the end effector with respect to I as written in I. Okay, there are two ways. Addition of vector angular velocities individually by projecting them back all into I frame, or using that formula. Two ways. Now there is one more formula that you saw here, and I would like to explain that to you before we're finishing this video, and that is the second one. So here is omega of end effector with respect to inertial in inertial. Sometimes they want omega of the end effector with respect to inertial, but as described in what? As described in the end effector. So it depends on what you want, whether you are getting something from a sensor or you're reporting something with respect to an inertial frame or so on. Sometimes you want this omega, actually, not this one. Well, how can I convert them? Well, it's not a hard thing. If you look at the relation here at the top, you see they are quite similar, except that here is R dot R transpose, here is R transpose R dot. So it seems like the order is reversed. If you reverse the order, you get omega of the end effector with respect to inertial as written in end effector, not as written in inertial. Where does this formula come from? Well, if you remember, here I'm after omega of E with respect to I in E. How can I find it from this guy that I already have? What's the relation between these two? They are both the same entity, just described in different frames. How can I go from one frame to the other? You know, you need the what? A rotation matrix of this frame with respect to this one. So what happens if I do it? It is going to be a rotation of EI. And for this one, I'm going to bring this relation down here, which is R dot EI times R EI transpose. Yes? Of course, with one caveat. What is it? I don't have omega versus omega. I have what? I have S of omega versus S of omega. Correct? So you have to keep in mind you're not really just doing omega and omega, you're doing S of omega and S of omega. So the change will be like this. So we have to pay a little bit of attention here. That here, what you want is this. Now for that, I write what I just had. R of I with respect to E times omega of EI in I. Good? This is what I have. Yes, this is what I have. And now what is this one? What can I do with this one? How can I go from here to here? Well, first, let's replace omega. Can I? No. The problem here lies in the fact that I have S of, not omega, it's S of R omega. And this R is not a constant, so I cannot use the linear property that I learned. Where is that? Here. I cannot use this linear property here. What I can use is this guy. That S of RA is what? RS of A R transpose. I'm going to using this property. It is RS of AR transpose. So look, this is S of RA. Here A is like our omega. So it is again going to be what? RS of AR transpose. So it is going to be R S of A R transpose based on that similarity transform property. And now for this S of omega E in I given written in I replace this formula. Okay, so this is what? This is R dot R transpose. Is that right? Let me make sure I did not make any mistake. This is S of that is right. That is also right. Good. R of I, E. Oh, there we go. Yeah, that is right. Good. Okay. R S of A R transpose. R S of A R transpose. Good. And for that, I used the exact same thing, R of E with respect to I transpose R dot. Everything is right. Good. So now, if you expand this, what would you get? Let me expand it forward. You will get R of I with respect to E, R dot of E with respect to I, times what? Times R of I E transpose, R of EI transpose. So what is this, if I ask you? What is this one? Well, this is transpose of A times B, so I can reverse the order. It's going to be the transpose of this one, basically. And what is this one? What is the rotation matrix times the basically the inverse of it? You know that is I identity, and transpose of identity is identity. So that whole thing is I. So I can just take it away and it becomes what? R of I E R dot of EI. Correct? That's what I have. And now I have to show that is the same as this one. REI transpose. And it is, because this guy here is what? This is R of E in I transpose times what? RE in I dots. And this one is exactly this guy here. So here I got both of my formulas. That if I want to calculate omega of the end effector in base, written in base, I do R dots, R transpose. If I want to calculate omega of the end effector with respect to base, but written in end effector frame, I reverse the order. It is going to be R transpose, R dot, okay? And you see both of them can easily be proved using this important property of what? Of the rotation matrices and the skew symmetric operator. Okay, so here I did a little bit of cleaning because I just wanted to have my formulas in the nice manner now that I have proved everything. So these are the two very important formulas for angular velocity of end effector in base as written in different frames. And I showed you that in order to get this one, you can either use this formula or use the method I called the vector addition method, and you saw how I used it, right? Good. So now one last thing is quaternions. As I told you, in navigation especially, and in applications that you don't want to fall into the singularities of the Euler angles, we use quaternions because mathematically they don't have a singularity. And if you remember, I told you for quaternions, the R of the end effector with base, or one frame with respect to other, based on the 4 Q values, can be written like this, right? Just watch my video on quaternions and you'll see the rotation matrix over there. So if I use this rotation matrix and I plug it into the formula for omega of the end effector with respect to the base as written in end effector. Okay, so I plug it into the formula that I just proved here for you, and I get this entity here. If I do it, then you can easily show that the omega of the end effector with respect to inertial as written in end effector can be written like this. 2 times this matrix times all of these Q dots, okay? So this is a 3×4, that is a 4×4, so the 4×1, so the result is going to be a 3×1, which is this guy here. Okay, so it's not hard to show, it's just chain rule and reformatting it into this version. Good. Now, what I will do is I will add a 4th row to this version here, and for that I will add a vector 0 here, okay, just so that I can write the whole thing as a 4×4, not 3×4. So what I did here is the first 3 rows of this matrix, if you look at the first 3 rows, they are exactly these guys. I added 1 extra row when you multiply that row by this column of Q not 0 dot all the way to Q3 dot, the result should be a vector 0. Why is it? Just take a look. If I multiply the last row of this matrix by this column vector, what is the result? It is going to be 2q0 q0 dot plus 2q1 q1 dot plus 2q2 q2 dot plus 2q3 q3 dots. Why is this equal to 0? Well, the answer all lies down to this, that the magnitude of the quaternion Q, which is what? Q1 squared, Q not squared, I'm sorry, plus Q1 squared, plus Q2 squared, plus Q3 squared. This magnitude is equal to what? To 1, right? That's unit quaternion. Now take a time derivative from this. What would you get? The derivative of this is going to be 2q0 q0 dot. This one, 2q1 q1 dot, and so on, and derivative of 1 is what? 0. That's exactly this equation here. So you see where I got the last row and this vector of 0. Okay? If I write it that way and I form everything into this 4x4 format, and I basically add an extra 0 here, right? Then I will get this relation. Now, why did I do that? Because my goal is to go backwards. Here, I assume that I know my q dots. I want to find my what? My omega, correct? So here, I know I need to know my q dots and q's at any point so that I can calculate what? Omega. The matter of fact is, in navigation systems, it's the other way around. Okay, so let me show you that. Okay, here I did some cleaning as well. In navigation, what you really get from your sensors, most of the time you use gyros to determine angular velocity of your platform, right? Angular velocity is coming from gyro. They are what? They are these omegas. Now, and that is the importance of why is it in E. You might say, why did you go with the omega of E in E, not in I? That's because of the way the sensor works, right? When a sensor measures the angular velocity of, let's say, the helicopter, right? It is, and writes it as, hey, it is like 2i plus 3j plus 5k. What do you think the I, J, and the K are in that case? Are they the I, J, K that are attached to the helicopter? Are they the ones for the frame attached to the helicopter? Or are they the ones that are attached to the inertial frame, let's say, on the ground? Well, that's, of course, it is with respect to what is attached to the helicopter, right? When a sensor is attached to a rigid body, when it measures something, the measurement are always described in what? By the sensor, they're always described in the body attached frame, not the inertial frame, because the sensor itself is not inertial. So it can never describe anything in inertial frame for you. If you want to take it to the inertial frame, you have to use a rotation matrix yourself multiplied by this. Okay, but a sensor always measures in its own frames, and if it's attached to the body, it means it is measuring in the body frames, the body attached frames. So this is what your gyros will measure for you. So they are coming from gyros. Good. Now what do I need? I need my q dots. As I said, I need to go backwards. Instead of knowing q dot and q find omega, now I know my current q's. I also get omegas from my gyro, and from this I can get what? My q dots. Can I get my q dots? Sure. If you see here, q dots are what? You divide both sides by a 2 and then multiply by inverse of this guy. Okay? If you do that and rewrite it nicely in terms of the components of omega, which here you called omega, x, y, and z, And in terms of the Q's, this is the way to describe the Q dots. If you want to write it in a matrix notation, you can say that Q dot is equal to what? Is equal to 1/2 a matrix 4x4 formed from omega components, which here you're showing with cap omega, times the quaternion Q. This matrix can easily be determined by the measurement of the sensor. So the sensor gives you this cap omega. Q, you know at this moment, so you can find what? Q dot at this moment. And when you know Q dot at this moment, it means if you integrate them, you can get what? Your next Q values. Correct? And you know Q quaternions means what? Quaternions means rotation. Correct? Quaternion, each quaternion can always be what? As you can see here, each quaternion can always mean a rotation matrix for you. So whenever I know my quaternion, I can exactly find out what is my rotation with respect to what? With respect to, let's say, the inertial frame, the Earth, or whatever you consider inertial here. So if I know my quaternions at all times, I can find my orientation of the, let's say, the helicopter or airplane, whatever, with respect to the Earth. The question is, how do I get what? How do I get them updated? Because when I move and my sensor shows some non-zero numbers for this omega x, y, or z, or all of them, how do I update my Q's? And this is your update equation. This is your quaternion update equation. Correct? Because Q dot means what? Means the limit of delta Q over delta T as delta T goes to 0. Correct? So it means what? If you approximate it, it's approximately equal to delta Q over delta T, where delta T is small. And delta Q means Q at the next time point minus current Q. So if I know my current Q, if I know my current Q dot, which I can get from this equation, if I have a sample time, and if I have measurement of omegas from my gyro, I can plug them here, I can get my Q dot, and with all of that, I can solve for what? My next set of Q values, right? So if I start from some initial Q, which comes from the initial angles of the airplane, let's say when it is on the ground, by reading the gyro values all the time, the omegas coming from gyro, and with the sampling time, you can keep updating your quaternions, which means you can keep updating what? Your rotation matrix. So you can always keep track of your angles. And here, I'm using quaternion to make it happen. I'm not using what? My Euler angles or other representations that have singularity. And that's the power of the quaternions. While I keep updating them, I make sure I'm not going to face singularity in these calculations, okay? So this is one of the applications also. Okay, so hopefully I could convey to you the notion of skew symmetric matrix, where and why it shows itself in rigid bodies and in robotics, because as you can see, it is the skew symmetric of the angular velocity is related to the rotation matrix. So through rotation matrices, I can get my angular velocities, or I can use this vector addition method to get my angular velocity of what? The end effector, okay? This is the first step toward going to finding the complete set of velocities of the end effector, because you'll see that end effector has two sets of velocities, linear velocities and what? Angular velocities. Okay, and we describe the angular velocity for you here. Linear velocity, I guess everybody knows from physics or dynamics. It's the way that we describe angular velocities and in matrix notation and related to the rotation matrices. So once I know this, next step, I'm going to talk about manipulator Jacobian and show you that how you can relate your joint angular velocities to the end effector, linear and angular velocity through that Jacobian matrix. Okay, thank you so much for your attention. See you later.